For this presentation, the objectives are outlined as follows. At the end of this presentation, students will be able to define what crystalline solids are and distinguish them from amorphous solids. Students will also be able to explain the internal structure and particle arrangement of crystalline solids, classify them based on their bonding types, and describe their main properties. Finally, students will be able to relate crystalline solids to real-life and industrial applications. Matter exists in different states such as solid, liquid, and gas, and solids represent the most structured form of matter. Among solids, crystalline solids are unique because they are particles and arranged in a highly ordered and repeating pattern. This long-range order greatly influences their physical properties such as melting point, hardness, and electrical conductivity. Understanding crystalline solids is important in chemistry and material science as it helps explain the behavior of materials ranging from simple salt crystals to complex structures like diamonds.
First, what exactly are crystalline solids? Crystalline solids are solids where atoms, ions, or molecules are arranged in highly organized, repeating three-dimensional structures. These structures or pattern doesn't stop halfway. It extends throughout the entire solids, forming that we call as a crystal lattice. Because of this long-range order, crystal solids have some very recognizable traits. They have the definite geometric shapes, meaning that their structure isn't random or messy. They also have a melt at a sharp and specific temperature, not gradually. Another key feature is anisotropy, which means their physical properties like conductivity or hardness change depending on the direction measured. Crystalline solids have an ordered internal structure. Their particles follow a repeating pattern which give them a sharp melting points and a regular shape. Classic examples include like sodium chloride, quartz, and diamonds. That material are structured to down their core. On the other hand, amorphous solids are the rebel. Their particles are arranged randomly with no long-range order. Because of this, they do not have a sharp melting point. They gradually soften, their shapes are irregular, and examples like glass, rubber, and also plastic. So basically, crystalline solids are organized and pieces, precise, while amorphous solids are disordered and flexible. To understand crystalline solid, we need to zoom into their structure. A crystal lattice is actually a three-dimensional arrangement of particles in space. Think of it as an infinite grid extending in all directions. Within this lattice, we have the unit cell, which is the smaller repeating unit that represents the entire crystal structure. There are three main types of unit cell. The primitive or simple cubic, where particles are not only the corners, the body centers cubic or BCC, which has an additional particles at the center of the cube, and the face-centered cubic or FCC, where particles are located at the center of the face. These unit cell structures are not just theoretical, they directly influence the density, packing efficiency, and also stability of the crystal. Crystalline solid can be classified based on the type of bonding between their particles. Like first, ionic crystal, where positive and negative ion are held together by a strong electrostatic force, like sodium chloride. These are usually hard and brittle. Next, covalent network crystal, where atoms are bonded through a continuous network of covalent bond. Diamond is the perfect example, which is extremely hard and extremely stable as well. Then, we have metallic crystals, where metal atoms are held together by a sea of delocalized electrons. These explain why metals are good conductors and heat and also electricity. Lastly, molecular crystal, where molecules are held together by weak intermolecular forces. Because these forces are weak, molecular crystals usually have a low melting points. Each type behaves differently, and it all comes.
Crystalline solids are formed by strong electrostatic attraction between positively charged ion, called cation, and negatively charged ion, called anion. Because of this strong attraction, ionic crystalline solids are hard and brittle and have a very high melting point. They can conduct electricity when molten or dissolved in water, but not in the solid state. Common example of ionic crystalline solid include sodium chloride, which is a table salt, and potassium bromide. Next, we have a covalent network crystalline solid. In this type of crystalline solid, atoms are connected by strong covalent bonds throughout the entire structure, forming a large network. Due to this strong bond, covalent network solids are extremely hard and have a very high melting point. However, they are very pure conductor of electricity. Examples include a diamond and a silicon dioxide, also known as quartz. And then we have a metallic crystalline solid, consists of a metal atom held together by metallic bonding, where electrons are free to move throughout the structure. This allows metal to be good conductor of electricity and heat. They are also malleable, ductile, and usually have a shiny appearance. Examples of these metallic crystalline solids are iron and copper, which are commonly used in construction and electrical application.
Next, I will explain about molecular crystalline solids. Molecular crystalline solids are solids where the particles are molecules that are held together by intermolecular force. These forces are relatively weak compared to ionic or metallic bonds, which is why these solids have certain unique characteristics. First, let's look at their characteristics. They usually have a low melting point because the intermolecular forces do not require much energy to break. They tend to have a soft texture, making them less rigid than ionic covalent network solids. They also have pure electrical conductivity because they do not contain free ions or electrons to carry charge. Examples of molecular crystalline solids include ice or H2O, where water molecules are held together by hydrogen bonding. Next, we have iodine, I2, where molecules are held together by London dispersion force. Overall, molecular crystalline solids are known for being soft, easy to melt, and poor conductor due to their weak intermolecular interactions. Now, I will explain the properties of crystalline solids. Crystalline solids have a very ordered and repeating internal structure, and because of this, they show several unique properties. First, they have a definite melting point. This means they melt sharply at a specific temperature because all their particles are arranged in a uniform pattern. Second, crystalline solids show anisotropy. This means their properties such as refractive index, electrical conductivity, or hardness can vary depending on the direction in which they are measured. This happens because the arrangement of particles is not the same in all directions. Third, they have high symmetry. Their internal structure follows a regular geometric pattern, which gives the solid a balanced and well-organized appearance at the microscopic level. Last, crystalline solids have predictable cleavage plane. This means they break along specific flat surface where the bonding forces are weaker or more uniform. All these properties arise because crystalline solids have an ordered internal structure, also known as a crystal lattice. Crystalline solids play an important role in daily life and modern technology. For example, silicon crystals are widely used as semiconductors in electronic devices. In the pharmaceutical industry, the crystalline form of a drug can affect its solubility and effectiveness. Crystalline materials such as quartz and cement compounds are also commonly used in construction. Additionally, metal crystals are essential components in electronic circuits due to their electrical conductivity. In conclusion, crystalline solids are characterized by their order and repeating particle arrangement, which directly affect their physical and chemical properties. Different bonding interactions produce different types of crystalline solids. leading to a wide range of applications. Therefore, understanding crystalline solids is essential for progress in chemistry, industry, and material innovation.